somehow link that signal to connect with really powerful machines. And there are components that does that very well. So so if you really want to like activate a washing machine with an Arduino can do that with the right components. Because a signal is a signal. A signal to drive a plane is the same signal to drive a robot. I think it is, but still, the signal basically doesn't need a lot of like big power to tell you a 1, right? You just need little tiny voltage to tell you that, oh, I'm telling you it's 1. Digital information. Yeah. So, and for Uno, there are similar stuff where you have the same size and different shields. This one for sensors, similar to here. And this one is what we call a CNC shield. CNC shield is basically the same ones here, but they all of their power is focused on controlling stepper motors. So who knows what CNC is? CNC. Okay, what? CNC, it means computer numerical control. And many of the industrial machines has always been CNC. You know, we ask a machine to do this and that in automatically. It requires computer control using data, not like a guy switching it 24/7. And a computer does that. Any machine that relies on data to feed it with instructions is a CNC machine. And but nowadays these sports, many of us makers refer to CNC machines as like a laser machines, where you use motors to control the motion of a laser, to shoot out beams of laser, to cut stuff, to engrave stuff along an XY axis. So that's a CNC. And if you want to mount a drill, keep spinning, and then you also use the same mechanism to use this board to drive similar motors or bigger motors to move along multiple axes, either 2 axes or some crazy people, or I mean industries have been doing it for a long time, but some of the really amazing makers, they started to apply stuff in their own ways. But anyway, this is a CNC, like a drilling stuff, cutting stuff. It's also a CNC. So that's a CNC shield. It uses the data process from a Uno to drive motors. That's basically it. And there's a motor shield. I'm not familiar with this shield actually, because it drives a lot of all the little self-driving cars, little moving robots using the motors. And it operates on similar logic, process signals, and then turn it into electricity to pump it to motors, or pump it into moving devices, heat up stuff and stuff. So all sorts of possibility. Now here's another, the level is, so after having processors and having shields, you would have what you want to do with those information and all those process information as outputs. You would, for robots, in this case, you would turn it into motions. And for motions, you need, the very basic ones would be motors. So motor would turn electricity into, via magnets, they would generate motion. And who has seen a motor like this before? If you have dealt with like remote cars, then you would actually use one. The cheapest motor out there, it's I would call it like a dumb motor, like a stupid motor, because it knows nothing. It just spins and keeps going forward. It doesn't know stuff. It doesn't know anything. Okay, so I just have a few of these here in case anyone in the future will want to play with them here. But the very common motors that I use is motors to achieve precision. So motors can, you would tell it to move. You want to move something 10 centimeters forward. You would actually need to translate that and tell the motor move exactly 10 centimeters. Not 10.1, not 9.9, but 10. You want exact precision. And this is where these motors come in. and these are the very common ones for entry-level builders. In fact, some of the machines out there, expensive toys, they also use these tools inside. And for motors to generate motion precisely, there are two types, and I will first go into stepper motor. So this is the very basic stepper motor, and we call it micro stepper motors. So basically, this is a driver. So a driver would be responsible for telling stepper motor how to turn. Okay, and it processes information from the boards, and then use it to I don't know the exact details, but we need a driver to drive the stepper motors, because how a stepper motor works, it relies on the changing current of two circuits to achieve, so a motor can turn like this, and in precision. It requires frequently changing electric current, and we need a driver for that. So this is the very common stepper driver. You can use it to move little things precisely. Actually, people have built 3D printers using these motors, and it's impressive. And another very common stepper motor is these what we call NEMA 17 motors. You can Google it, NEMA 17. It became very like the standard because all 3D printers uses them to achieve precision. And a stepper motor like this one, it moves 1.2 or 1.8 degrees per step. I don't know the exact degree, but for a motor to spin around one time, how many degrees is in a circle? Oh, I'm glad you guys know. Okay, so one circle is 360 degrees, and for a motor to spin an entire circle, this motor takes 200 steps. So if you later on you can touch it and feel, you move it a little bit, you hear a little click, and that's one step. And it takes 200 steps to move this motor one circle. Okay, I'll pass it around so you can get a feel. Okay, and this stepper motor also needs a mechanism, needs a device, a component to drive it, like this one, a driver. And this little piece here can handle small stepper motors like this one, and it became very cheap because of the rise of 3D printing. All 3D printers uses this component, and many manufacturers started pumping these in mass quantities. So they are very reliable, very cheap, very stable, and we use these to drive stepper motors. So like in different weights at all times, it will be able to change its current to drive stuff. Back to the stepper. Where's that stepper? The disadvantage of that NEMA 17 stepper motor is if it's too heavy, if something is stuck or the gears are not connected properly, when it will actually lose a step. Meaning, I tell the motor to move 10 steps, because something is in the way, something is stuck. It only moves 7 steps, and it lost 3 steps. We call it losing steps. And for stepper motor, if you lose a step, you don't know, unless you're there to hear the little click. You don't know if it lost steps. So it is what we call an open loop motor, meaning you just feed it, you tell it to go 100 steps, whether it's 100 steps or whether it went 80 steps, you don't know at the end. But servo is different. Servo is, if you tell it to go that amount of degrees, it will actually go that amount of degrees or it burns out. And like I said, this is 9-gram servo. The size is already standardized, so all the stuff you find, all the projects out there uses these, from model planes, model helicopters, maybe robots or facial recognition, self-tracking robot cameras, uses this motor. And I bought 2 types here. this one is the weaker one. They are similar price, but this one has less torque. Who knows what torque means? Torque, okay? Torque is the ability for a motor to drive something, like how heavy you can drive. Like if you pull a rope on a motor and the motor spins, the torque is like how much weight it can actually pull you. So torque, all sorts of different motors have torque ratings, and this motor it has less torque than the other one because this one uses plastic gears, this one is metal gear, but it's heavier, so give and take, you choose what you want to do with these servos. Now this one I also bought quite a few because they operate on similar principles and similar signals, and they can lift a lot heavier stuff. But of course, servos get bigger and bigger and bigger. So you can see a lot of like on the TV, like those car building robots, they operate in another level. So as long as you feed enough electricity, you know the theory, then yeah, you can build pretty big motors and still drive it with computers. Okay, so these are about like you have one problem and then you find a solution and you drill deeper into the solution. You found another problem and you drill into deeper solutions, and that's all about. That's what learning is about. Is just finding solutions to your problems. So what I do is it's called crimping. Who has heard of crimping? Crimping wires? Okay, you're an expert. Crimping is basically turning a wire into a terminal, like a connection. Yeah, can I? Yeah. So basically, and you get to learn a lot of wiring in the future. But these wires are perfect for transmitting signals. These wires are perfect for communicating from your processors into the sensors, and they're fine. But many of these wires you have to check. If you want to power it with like bigger motors, they may not be able to handle the amount of current. So there will be a fire hazard. But these devices, these wires are just fine. Okay, and okay, what else? Mechanical, right? So buying an Arduino, buying some sensors, wire them together. I mean, as you learn it's quite simple because there are many tutorials, many YouTubers, many platforms to teach you how to code, how to wire, how to make something. But if you want to actually build a proper looking, nice looking machines, you need things to join everything together, and that's where parts come in. And parts is where 3D printing is good at, because 3D printer can print any parts you want in plastic. Of course, they come in different qualities and structure and stuff, but in general, they give you good parts for you to build robots, build cars, build whatever. Of course, not like really heavy lifting stuff because they're plastic, they crack. There's a limit. But if you want to build like little toys, little machines, and some people actually build like a robot arm this tall, with this long, with 3D printed parts, and it's fine. And they give you good parts to work with. And I will share some parts with you so you can pass around to see the quality, to get a hands on what 3D printed parts mean. Maybe you can pass around, feel it, see what 3D printing is. Who has heard of 3D printing? Heard of 3D printing? Great. Who has seen a 3D printer? Okay. Who has printed with a 3D printer? Who has a 3D printer? You're the hero, huh? Okay, so a 3D printer has reduced in cost significantly in the past just 4 or 5 years. They were used to be like, I don't know, maybe a few €1,000 machines or maybe even higher, used by factories to build prototypes. But there was a little bit of history, maybe if we have time on 3D printing. A bit of history in 3D printing. History of 3D printing. Okay. So why did 3D printing became so cheap so quickly? Is because it was an educational project in the United Kingdom where they started a project called Rapid Prototyper. What we call RAD is they made everything open. They started designing stuff, and then everything is open source. And then you would have producers from Europe, from China, from everywhere, just building new prototypes, machines, new 3D printers. And then the market is filled with all sorts of 3D printers for users to play with. So a 3D printer actually works in well, 3D, 3 dimension, 3 axis. Normal printer, when you print a paper, you go through paper printer, goes through the ink cartridge. It's 2D, 2 axis. It goes x y x y x y like that. That's 2D printer, like all of us have used before. And for a 3D printer, it basically after one level, it raises another level, and it raises another level, it raises another level until your object is complete. So if you're talking about like an object this tall, like maybe 10 centimeters, every layer is 0.2 millimeters tall. So maybe 10 centimeters, you would have 1,000 layers. So a 3D printer would actually do 2D printing 1,000 times to give you an object that you want. So that's 3D printing basically. And there are different methods and different materials. So, but the whole concept is similar. And 3D printing basically turns, at least the very basic entry-level 3D printing turns plastic into objects. So it does by, the raw material is, they come in like a pasta, they're like spaghetti, little strings of plastic. And what it does is basically it uses a motor to carry that, what we call filament, or raw material, filaments, into a heat chamber, like a heating device, to heat up the plastic up to a certain point that it melts and turns into liquid. And then as it turns into liquid, it moves along your machine with motions generated by stepper motors like the ones you're seeing. And it's basically that idea. So turning solids, plastic into liquid in very short time, move the machines across a fixed area, and as they cool down, they turn into solid again. And after a few hours of repeating this process, you have a 3D printed object. And you need 3D printing to do all sorts of stuff because they give you the objects that you need to build your machines. Okay, and later on I'll go through the robots that I've built. They are all 3D printed, and the beauty is a 3D printer, you can get one for the cheapest one. You can get it for less than 200 euros. But you have to learn the process. You have to, because 3D printers, many people don't dare to get into 3D printing because it's actually quite a painful learning process because they break down easily. When the plastics gets too hot, or if you don't do it right, they actually melt and get stuck, and then your parts are like, you have to change parts, you have to tune the motors, you have to tune the platform. It's quite a bit of work, but I assure you, if you can master 3D printing, the possibilities are endless. If you are willing to pay the effort to learn about 3D printing, you can actually make a lot of stuff. You can make robots, you can make all sorts of machines, and it's beautiful. We need to tell the board that, okay, you have an LED light, and we need to use it as an output, okay? You have to tell it pin mode. Whenever you use a pin to output something, to give out something, you have to define the pin mode as whether it is an input or an output, okay? But since we're not using pin in this case, we are just using an LED light. inside the loader of the Arduinos, they have some kind of infrastructure underneath. There's a part called LED built in. Okay, so this is the pin mode. You have to do a bracket and tell it, okay, we need to use this pin. LED built in is a built-in pin. And we need to set it as an output device. Output, okay? And of course, every C++ code, don't ever forget the semicolon. Yeah. I have failed loading programs hundreds of times because I missed it. Okay. So that's it. When a board activates, just tell it we need to use your LED pin as an output. This is what we're telling the board to do. Okay. The next part is the loop. The loop is okay. Now I've got a pin. I've got an output pin or LED. What do I do with it? You have to tell it, okay, as the board, you need to write a 1 to this pin. And the instruction in the Arduino in C++ is to tell it to digital write, okay? And then you refer to this as well. This is the name of the pin for an LED. It's built inside. That's why it's called LED built in. So you refer to this pin as a LED built in, and now I'm telling you I'm writing something to this pin. From a board perspective, writing something means giving a 1, giving a signal. It's writing. LED built in, and then you just write high. You write high, either high or low usually. Okay. So this is one line, and of course don't forget the semicolon. So what happens in this loop is, right now, before I add on, it simply sets up that pin, and then it just gives a 1 to that pin forever, okay? So it just stays on. So what happens is, I actually want to blink, and then hold it for a while. So now the pin is a 1,